Heat and thermo homework, numbers 9 through 12. In number 9, I have an ice palace coming into contact with steam. And so the steam is melting the ice palace, and the steam is liquefying as it does so. So the steam is actually losing energy, while the ice is gaining it. And so there's no temperature change going on here, so the only energy that can really be absorbed or transferred is the energy that occurs during the phase change. So the mass of steam has to do with the latent heat of vaporization, and the ice has to do with the latent heat of fusion. And so the mass of the steam is what we're looking for. The latent heat of vaporization is 2.26 times 10 to the 6th. The mass of ice that's given to me is 4.9 times 10 to the 6 kilograms. And that latent heat of fusion is 3.3 times 10 to the 5th. So when I multiply on the right and divide by the latent heat of vaporization, the mass of the steam that's required is actually just 7.2 times 10 to the 5th kilograms of steam. So number 10 is kind of different. It wants me to solve for the heat of fusion of gold. So that's LF. And it gives me, for a bar to melt, it needs to absorb 2.5 megajoules of energy. And so if we know our SI prefixes, mega means that this is actually 2.5 times 10 to the 6th joules. So I use that as my energy, and then my energy has to be divided between heating the gold up and also melting it. So the mass of the gold that I'm heating up, that bar, is 12.4414 kilograms. The specific heat is 129. The final temperature is 1063 degrees. The initial temperature is 5. And again, the mass is 12.4414 times the latent heat of fusion. And so when I do the math and I solve for my latent heat of fusion, you should get somewhere around 6.45 times 10 to the 4th joules per kilogram times degrees Celsius. And that's actually wrong. It's not times degrees Celsius. It's just joules per kilogram. Number 11 has to do with the first law of thermodynamics, and that states that any change in internal energy of a system has to do with heat added to the system minus work done by the system. So anytime I have a delta anything, that means final minus initial. So I have my final minus my initial internal energy is equal to work or heat added minus work done. So I'm given my initial internal energy is 42 kilojoules or 42,000 joules. The heat added to the system is 4 kilojoules of energy, so that's 4,000 minus the work done. Now, work from last semester can be thought of as change in potential energy. And remember, potential energy was mgh. So here, the work is just mgh. So that becomes 227, or the mass of the snake, times 9.8, times its height, which is 8.45 meters. So solving for final internal energy, you get 27,200 joules, or you can write it as 27.2 kilojoules. Number 12 has two parts, one being energy heat transfer and the other having to do with the first law of thermodynamics. So if we solve part A, It's talking about how much energy must be transferred to decrease temperature. So if I'm changing temperature, I know that I'm dealing with specific heat. And so in this case, the energy needed is the mass of the jelly, which is 4 times 10 to the fourth, times the specific heat, which we say is assume the same of water. So that's 4,180. Then the temperature difference. The temperature difference is 20 degrees. And so if we solve for that, we get 3.34 times 10 to the ninth joules. Now you could be asking me, why didn't I make this negative 20? Well, I didn't make it negative 20 because I know that whatever I get for my answer, I know that is lost because I'm decreasing temperature. So now to solve B, I need to use the first law of thermodynamics. Change in internal energy is equal to heat added minus work done. And so my change in internal energy, the heat added is not really added at all. It was negative, so it was lost. So it wasn't heat added to the system, so it has to be negative. So it's a negative 3.34 times 10 to the ninth joules. That's going to be minus the work done, and it is done to the surroundings. So it's still negative 1.64 times 10 to the ninth joules. And so when I subtract these two, my net change in internal energy is a negative 4.98 times 10 to the ninth joules.